thanks for the introduction, Saif, and I'm happy to be here to give you a brief overview and share some perspectives that I have on big data management and in particular on Apache Flink. But maybe first some words about me. So I consider myself to be a innovator, and what that means, I conduct research that hopefully will result in groundbreaking technologies. That's always our goal. And then those inventions that come because of having researched those groundbreaking technologies should, of course, become innovations. And that's something that is very important, also in particular for places like the EIT, where it's an Institute of Innovation and Technology, right? So that is in order to become entrepreneurs, focusing on creating some technology through hopefully groundbreaking research and then capitalize on it, making it innovation that will be used eventually either in existing products, enhance those, enhance the quality of experience, performance, cost, whatever, or by really creating new companies, startups. And maybe a couple of words about my background before I go into details. So I said, by heart, I'm a technologist. I did work in computer science, in particular programming languages and exception handling, also in data management and multidimensional indexing. That's where I got my PhD. I was quite some time in Silicon Valley, where I worked at the IBM Almaden Research Center in the areas of self-tuning query optimization, machine learning, and information integration. And have a couple of other functions nowadays, like in Toronto, but also with some big data initiatives in Germany. And I've been creating a couple of technologies that are used by IBM, Oracle, Microsoft, SAP, several patents, and also been involved in several startups in that field. But with that, let's talk about the topic at hand, and that is big data. And all of you in the summer school and even before the summer school already have heard about those big buzzwords, that is those V's, which is a really funny thing, by the way. So that Gartner started with those V's, volume, velocity, variety, that all of you have heard about. And that's what originally used to define big data in the beginning, like in 2008, 2009, 2010, when most people didn't even know the term. Then, of course, as anything that follows a hype cycle, and if you know the Gartner hype cycle or others, right, you'll notice that, then a lot of other people want to capitalize on the hype. And that means the important thing is, in order to capitalize on the hype, you define whatever you're doing to be that as well. The same happened with cloud computing, and the same has happened in big data. So nowadays, everybody who can come up with a letter V, a word with a letter V, can add it to the mix, and it's big data, so it's kind of nice. You have, the next thing is IBM added the word veracity, because yes, you're dealing with uncertain data, and they had some products there. Then came the visualization community, noticed, well, we also have a V, so we are part of big data. Then now the big problem is the business community was shocked. What can we do? Well, we have value. So we are also part of big data. It's fantastic. So as long as you're V, you're part of big data. No, but let me stop my rant now. What's really about big data, if you just look at the three V's, it's actually missing the point. And that's what I'm trying.
We have a V here, Volker.
Actually, the interesting thing is, you're not the only one who told me that. So actually, the German Trade Ministry, they told me the same. We are happy we have another V. So they said the same, but I was not going to say that. So what's happening in big data actually is we are dealing with a much larger complexity in the data and the analysis. And that's also one thing that yesterday has been drawn a little bit of attention to, but I want to highlight that again. It's not just about the data. The data itself is actually pretty much useless, meaningless. It's really about what we do with the data, and that's the analysis. And that's what I want to focus on a bit more. Because also, if we talk about the three V's and we talk about regular analysis, then there's not really a problem. So let's say from a technological perspective, a lot of people would have said, you know, big data, those three V's, we cannot really manage them very well. So big data is anything that cannot be done with current systems. You often hear that as well. And with that, a lot of the analysis technologies are missing the point. Because if you do things like your standard reporting that you would do in your standard business application, like aggregation, selection, and so on, like the reporting tools in an SAP application, that actually can be done on petabytes of data, and you don't need Hadoop, you don't need a data warehouse, you use your standard database. It actually does work, it has worked for a long time. So the volume of the data, if you do simple analysis, is not really that much of a problem, including things like SQL queries, XQuery, and so on. If you do that, in many applications, your best choice is still a relational database. And we want to be very clear about that, because if there's this hype of big data, a lot of people tend to forget that there is a technology that is more than 40 years old. So I'm the secretary of the VLDB endowment, the endowment of very large databases, that is going into its 41st year right now. And those technologies are very, very valid for a lot of applications. And we should not forget that. There's still a place for the Hadoops and Sparks and Flinks that I'll talk more about soon. But when I do consulting for companies, it's very clear to point out there's a lot of places when those technologies have no place whatsoever, even though the Clouderas and others want to make you believe differently. Think twice. And a good example is scale out. So systems like Hadoop and so on, they work very well when you run them on hundreds or maybe thousands or more of computers. If you have only 3 or 4 or 5 servers, you sometimes may want to think twice if you really need that. But more importantly, if your analysis is not too complex. And that's where it gets really exciting, because that's where, for me as a researcher, for me as an innovator, the real change, the game changer is in big data, and what really makes it exciting from a technological perspective and also from enabling new applications, which is always the holy grail of research, right? You can do research in 3 dimensions. Either you enable new things, or you increase the performance, or you reduce the cost. But enabling new things is the holy grail, and there you can do things. And what are we doing? What's the new things that are happening? It's because of those 3 Vs. If we do more advanced applications, and more advanced applications come from advanced algorithms, like some of the ones you will hear from Jeff Allman. You heard initial ones yesterday already, but there's more coming during the next days, that are doing data mining, doing predictive or prescriptive analytics, that are applications in the area of signal processing, in the area of machine learning, in the area of text mining, and so on. Then the game is actually changing, and I'll tell you why in a second. But it's important to point out again, and that was also said by Jeff yesterday already, it's not just about machine learning. That's another hype, right? So it's actually way beyond machine learning. Signal processing is important, text mining is important, et cetera, et cetera. But what's really changing here? What's changing is that traditional data management systems, so everything that you know with SQL, relational is based on a concept called relational algebra. The relational algebra consists of a few basic operations. You hopefully all know them: selection, projection, union, intersection, and Cartesian product. And you have some derived operations like join and whatever. And those operations are not sufficient in order to process those advanced data analysis algorithms like graph analysis or machine learning algorithms. And that's where the game is changing. We know how to massively parallelize selections, projections, and everything that's in the relational algebra. For that, you don't need Hadoop or any of those other platforms. However, as soon as we're going into those other domains, we get into challenges. And what's the key difference? And I tried to write that down here a little bit. So if you look at standard reporting, ad hoc queries with relational algebra, or even ELT, ETL, you scale very well with things like MapReduce, with SQL, XQuery, or aggregation selection. That's kind of good choices for those particular applications. If it's about real data mining, about those advanced algorithms, most people write them in a non-scalable way. And that's, if you attend the machine learning class, for instance, you will notice that you use systems like MATLAB, R, or Python to describe, in essence, iterative algorithms, algorithms that have a loop. So that's a lot of those machine learning algorithms are like that. And those iterative algorithms, we don't really know, and actually in the past, in data management systems, we didn't really know how to scale them to petabytes of data. The key goal of data management is to pass over the data once. Maybe if you do a 2-phase multiple merge sort, you pass over the data 2 times or 3 times, but no more than that usually, which is okay for a petabyte. But how do you deal with your iterative algorithms? So you need to massively scale out, and you have all those other aspects. And we learned about Hadoop as an example. But we also, and you have yesterday probably seen already some aspects why actually Hadoop may not be a good solution for some of those cases. So Hadoop is very good, and the speaker yesterday also said that for things like ETL or ELT. So if you have a large amount of data, you want to do data information extraction, you want to do data cleansing, those kinds of things, you have a record at a time operation. For every record you do something. That works pretty well because you can scale it out. That's called embarrassingly parallel problems that you can do. And you can also do an aggregation very well, so grouping things together. Because Hadoop, what it does, it's a very efficient implementation, massively parallel implementation of a user-defined function and a grouping sorting algorithm in parallel. So that's what it can do. And any problem, and Jeff Allman, I would expect, will talk about it because that's one of his also major areas of interest. how you can express a lot of data analysis algorithms by grouping and sorting, because that's what Hadoop can do. And if you're doing anything beyond grouping and sorting, Hadoop will get you into trouble. So that's to make it very, very simple. Okay, but there's another problem, and the problem is the complexity. And Saif was alluding to that, and yesterday people were talking about that as well. And I always, when I describe that, I like to talk about the problem of data science. You know, data science has become a new buzzword as well, right? So big data is going a bit down, and data science is reaching a little bit more of the top. And when you talk about data science, every good and even many not so good universities nowadays creating their data science programs. And what data science really means, if you want to do it seriously on big data, then you have to have different kind of competencies. And that's also some of the competencies that we are trying to teach you in the summer school. So the first competency is you need to know about scalable data management, because we are dealing with big data, fast data, high velocity, and so on. You heard about all of that. So you need to have skills like this. And some of those are pretty annoying skills, and many of you may not be that interested in those. You have to worry about memory hierarchies, about parallelization, about fault tolerance, memory management, and so on. You have to actually do something which people often would call systems programming. And this is a little bit cumbersome. At the same time, because we are dealing with those advanced algorithms, you have to have the mathematical skills, you have to have the ability to model the problem accordingly and get insight. And that's really a lot of skills from the mathematical area, statistics, mathematical programming, linear algebra, and so on. So those two different skill sets are very, very heterogeneous. So the one type of people are there, if you wish, the hackers, the coders that are really good in systems coding. The other ones are the people who are abstracting and building mathematical models. If you want to be a data scientist, you have to have the intersection of both, and it's even worse. Because as a data scientist, you cannot conduct data science in a single isolation problem. You have to look at the application domain. So you have to know, if I conduct, for instance, data science in climate research, we talked about weather over breakfast today, right? So I've been working with climate researchers. You have to understand climate models and how those come about and the influence factors in order to do some meaningful analysis, like building some support vector machines. You have to do feature engineering for the climate models, which is very different from, I'm also working with material scientists, and with material scientists, you have to know about thermodynamics and various other aspects that are important to understand in order to build and interpret those models. So you have to have domain knowledge. So data scientists really is in the intersection of those three circles, which means a data scientist is actually not what Harvard Business Review is currently saying the sexiest job that's out there. That's what Harvard Business Review says. But I would actually say data scientist is really a poor person, because they have a lot of heterogeneous skill sets that they have to bring together, and there's very few people who actually can do that. And that's also what leads to the fundamental problem. The fundamental problem is that big data analytics requires systems programming. So you really have to know how to code things efficiently, hand optimize, hand tune things. And just for fun, but also to make a point, I made a count. And what I did is I just looked on a professional network, in this case LinkedIn, how many people say they know Hadoop. How many people profess on LinkedIn I have advanced Hadoop skills? Because you could say in first order approximation that might be people who know things like those here, indexing, communication, blah, blah, blah. And at the same time, I made a count how many people can do advanced data analysis. And the first order approximation, again, on LinkedIn here might be how many people can do R, MATLAB, so write their machine learning programs there. So that's, we would think, people that have those kinds of skills to some degree. And the fundamental issue is that the people with big data analytics skills is the intersection. And you can already see that's very, very few. Which means also those people are highly sought after, they get a lot of money, but also I have to disillusion you. So, because if you want to know that, you really have to know all of those things. It's not enough to just know your math. It's not enough to just know your programming. You have to know both. And this is what led several people to say interesting things. So the Wall Street Journal was saying big data's big problem is little talent. And there's obviously truth to that if you see that. And also Nelly Kroes, the former commissioner for the digital agenda in Europe, was saying we'll soon have a huge skills shortage for data-related jobs. And the big observation here that I'm making, and the big point that I'm making, and then I'll lead into some further technological aspects, is that we have really regressed. And we have really regressed bad. We have lost 40 years of work. Thanks to the likes of Jeff Dean and others, we have lost 40 years of work. And I am. So what has happened is that if you think back, history often repeats itself. And in data management, we had exactly the same situation in the 70s of the last century. What happened there is people were writing their programs in programming languages like COBOL, PL1, and so on, and they had to hand optimize everything. You had to hand optimize which index am I using, how I combine data, and so on. You would all write this kind of code. So some people may know that. Björn is actually shaking his head like that, so you remember, right? So pardon me? so that was pretty complex. And again, a lot of highly trained people could do that, but not too many, in particular for the market demands. And what then happened in the 1970s of the last century, Cord invented relational algebra, and that changed everything. Because what happened then is suddenly you could describe your data analysis program with a set of well-founded, principled mathematical operators, selection, projection, join, and so on. And other people, Pat Salinger and others, invented what's called query optimization, so that when you write this way and you don't worry about how to execute it, the system will automatically find the best way of how to execute it and worry about memory management, caching, parallelization, etc. So you actually had a technology that allows you to specify what you want, but not how to compute it. And the system would find the best way and best strategy. And that worked well for relational operations. And what that enabled is this made really the big data explosion, the data management explosion happen. Because of relational algebra, people were able to build tools like front-end tools that many of you know. On the one hand, BI tools like the Cognosys and MicroStrategies, or some sexy visualization tools like Tableau or so. Because all of those in the end create SQL that is then automatically optimized, hardware adapted, and so on. In big data, we are far away from that. We cannot do that. So you have to hand tune it, which means in order to unlock this billion-dollar market that will be creating toolings and ecosystems, we need such a declarative specification and language, because only then, on top of that, people can build those value-add tools that we need, so that you don't write your strange MapReduce programs and so on, right? Because this is obviously not the goal. And that's what we have lost. So actually what we need is the moral equivalent of what relational algebra was in the 70s. We need that for big data. So that's the fundamental challenge. And if we can do that, only then we will unlock the billion-dollar market that all those fancy market research companies, the Gartners and so on, are predicting, which is, in my opinion, right now not true. But a lot of them are dreaming. But it's good. That's their job. So that said, what do I mean by that? So this is a little bit a messed up slide on this laptop, but I apologize for that. So essentially what you would see is, just to give you an idea what I mean by what and not how, so describing essentially in a declarative way the code, if you would write a k-means clustering algorithm in a system like Hadoop MapReduce, this would be 486 lines of code. So I had a nice thing, I took the Mahout code here and put it 1 pixel font size. You would have seen the 486 lines, but this is kind of upside down, but it's okay. 480 lines, exactly, it would be. So, and that's interesting. So if you want to do k-means clustering, you have to write that code, and then it takes a certain amount of time to develop, right? That's obvious, so you have coding time. And then it's even worse, because the code is non-robust at runtime. And what I mean by that is, if anything changes, then you may have to change the code. And let me give you an example. I make it simple. I give an example from relational databases, because what they do is, it really depends how you sort the data. If you say sort the data in SQL, you say order by. But sorting the data depends on how large your data is. If your data fits into main memory, you will use what algorithm? What do you use to sort? Quicksort? Why quicksort? What's the worst case complexity of quicksort? N squared, so which is not so good, right? So either we play some tricks, or we do what? Or we use, well, merge sort in memory, in main memory is probably not ideal, because you are, yeah. So, but you know, something like heap sort is a very robust algorithm. If you are building a nuclear power plant control, you probably use heap sort. If you can afford the worst case complexity of quicksort and you play clever tricks with your pivoting, then you probably use quicksort in memory. And if you go to disk, you will use merge sort. And the optimizer will automatically decide that, but the optimizer will do much more. The optimizer will also decide if you combine multiple tables, in which order you will join them, which indexes use and which columns and so on, which is billions of different alternatives. It's actually one of the very few successful applications of artificial intelligence, is the query optimizer in the database system. But you have a similar thing in this setting here. So in this setting here, if you do k-means clustering, it depends how many cluster centers do you have. Also, you can be smart about some other aspects in how you feedback things in building, in iterating on your until you converge in your k-means algorithm, where you could use pipelining or building some indexes during those iterations. But none of those is considered here because it really depends on how large your data is. It sometimes depends on data distributions and so on. Instead of that, you're writing hand-optimized code that works exactly for one use case. So it's data, load, and system dependent. So that's how you do it in Hadoop. Now, if instead of that you would do it declaratively, and we'll learn a bit more about Flink, which is the first step in that direction. Flink doesn't achieve the vision completely yet. That's why we still do more research. But Flink is a step in that direction. But in Flink, you would get something like 65 lines of code, which has a much shorter development time. It's much less error-prone, you can imagine. But at the same time, also, what's even more important, the runtime is more robust. And what that really means is you are saving 2 times. You're saving the time once I develop my data analysis, how long it executes, which is for computer scientists an interesting thing, but in practice it's actually a less interesting one. The much more important one is how long does it take me to write the data analysis program, because that's the cost of the human. That's much more expensive, and as we know, humans are much less scalable than computers, so we have to worry about that part much, much more. And that's actually the development time. And that is, again, declarative languages. So that means if we could achieve that, and as at Flink, as we will learn during the rest of the day, is a first step in that direction, is instead of describing the how, really, I would tell you, I wouldn't say sort, I actually would say given a collection, subdivide that collection into halves, do that recursively until each collection size has a size of only one element. Compare those elements. If one is smaller than the other one, then flip them, otherwise keep them, and then finish your recursion. That's the how. Instead of that, you just say sort. That's declarative. And if you do that, then we would increase the base of human data scientists, since suddenly we get a chance of removing this black circle, and then data scientists hopefully have only to focus on the red circle and some of the application knowledge, right? So we are doing what data management had done in the past, hopefully for the world of big data. Also, if we do that, we will reduce the human latencies. And by that, I mean the time to write the code. And of course, there's a cost reduction, there's a reduction in the runtime, which is again what computer scientists love because it's what we can measure, but it's actually, systems are pretty good. So, I mean, if it takes, except for too many mission critical applications, if it takes a minute or 5 minutes, very often doesn't make a huge difference, or an hour and a half. So, what that really means is that what's really key and what's the big challenge is so if you want to, I like simple worlds, so that's something I learned from Mike Stonebreaker. Simple world means we have either small data or big data. Big data means the 3 V's. We have simple analysis or we have deep analysis. And depending on where you are, there's a certain set of tools you can use. Simple analysis with small data, we all use our spreadsheets, Excel, OpenOffice, Calc, or whatever. If you move into the world of big data, but you do still simple analysis, something like Hadoop is okay, ETL, UDFs is fine. Anything more, forget it. Similar SQL. SQL is actually allowing you to do more than Hadoop, but it's also limited to relational algebra. Whereas if you want to do the serious analytics, and that's what everybody talks about in big data, deep analytics, people use R or MATLAB if the data is small. And now the question is, what do you do here? And because that's really where the music plays. And in this area, as said, you will hear more about Flink also by Ufuk and Max later. So that's one example of a tool that goes in that direction. And it's not completely achieving what I'm describing here, and you will notice also why and where. But that's also what we are doing as our next levels of research and innovation. And with that, let me give you a brief introduction to Flink, and I will do it more from the genesis, from a historic perspective, the more hands-on systemsy aspects I'll leave to my colleagues here. But first and foremost, I should say I was probably one of the very first users of Hadoop. So I got exposed to Hadoop in the year 2006. So way before anybody knew what big data might be. And I was using Hadoop and was shocked. I was really seriously thinking, oh my God, what did Jeff Dean do? And the reason is, as said, the MapReduce is just a very simple, primitive programming model, which is also a huge step backwards from what we already had. It allowed you to do some seamless scalability. That was good. So it had some benefits, obviously, right? You scale out to tens of thousands of commodity machines. That's useful if you have that many machines. But other than that, it's a bit strange. And it allowed you to do one more thing. It allowed you to do schema on read. It allowed you to do very efficient user-defined function processing, which is very useful for ETL. At the same time, though, it had a lot of other deficiencies. And for that reason, I thought, hey, one can do that better. And then I felt, let's start something where you can improve on Hadoop. And I conceived a project in 2008 then, which when I moved to Germany at the University of Berlin, TU Berlin, a project that I called Stratosphere. Back then cloud computing was fashionable, thus the name Stratosphere. And because you always have to be buzzword compliant, very important. This system called Stratosphere was essentially trying to extend the MapReduce model, because I thought, MapReduce is just too tight of a corset. It makes sense from an implementation perspective. If you're a distributed systems programmer who wants to scale out, then you really know what you're doing, that's good. But if you want to make it usable, it's bad. So I found some partners in Berlin and we started that project. Then we actually created a community around it, and people in particular, also SAIF and people at KTH were getting very much involved, and really we had some great, and still have some great collaboration in various aspects here. And also others. And in 2014, because we got a good amount of traction, like companies started to use it, universities started to use it for education, we made it an Apache incubation project first, and then it was actually the fastest Apache project that moved from incubation to top level. And it has a relatively fast-growing community right now. And what I want to point out to you, in particular, since you yesterday learned about MapReduce, I summarized that slide, which is showing a little bit my misgivings of MapReduce, and that really motivated the original Stratosphere and then later Flink. Also, you will see also some of the things in Flink have advanced a bit further than from my original vision. So the observation is that MapReduce is an overly simplistic model. And the interesting thing is also Jeff Dean agrees with that. So I had a discussion last year. I was invited to the data management self-assessment summit that happens every 5 years. The database, so the leading minds in the database community get together and discuss what are the big trends for the next 5 years. And in this context, Jeff Dean was also there, and we had a chat, and he also agreed that, he would not do MapReduce again the way he did it. So that's also interesting. And Google, as you all very well know, has also moved away from MapReduce for various reasons. Still, there's a point, if you do ETL, MapReduce is a good choice. So let's also not get that wrong. And Hadoop is a very good choice if you have this large clusters with tens of thousands of machines and you're doing ETL-like operations, UDF processing, and so on. So, yeah?
Can you say for the students who is Jeff Dean?
Okay. So Jeff Dean is actually the key person that wrote the original MapReduce paper from Google. So he's a Google, what's their name, fellow, or so I think they call it fellow. Very interesting guy. So, however, I said MapReduce, so what are the big challenges or problems? So the first one is that MapReduce is a record at a time, a group at a time, single input model. That means you have a function map, which is essentially a second order function that takes as an input a first order function. It applies it to every record, right? Functional programming 101. So all of you hopefully grasp that even from your functional programming class. But the problem is, if you want to do data management, it's not enough to have record at a time and group at a time operations for single inputs. You often want to combine multiple data sets. So that means at least what you need in order to have a complete model with which you could do what the power of the relational algebra gives you, that you need a binary record at a time, group at a time operator. And that's essentially what one would call either cross or which is a Cartesian product, or you can do some form of join, like a match operation, which is bringing together multiple records, either record at a time or group at a time. And that's essentially what was missing from that perspective. So another thing is, if you have those operations, you can more efficiently implement them. Because what people are doing now, if you want to combine multiple inputs in MapReduce, you need to either tag your inputs or integrate a distributed cache, which limits your parallelization. And that's a problem, because the key promise of MapReduce was that you abstract from the parallelization and the cluster. So that means if I do map and reduce and I do nothing else and I don't worry about distributed caches or so, I don't have to worry on how many machines it runs. I don't have to worry about that. In that level, it's declarative, and that level actually achieves the goal. The problem is, as soon as I have two inputs, all of that falls apart and breaks. And the reason is that at that moment, I have to implement something which in database systems we call a join algorithm. And now the problem starts, because there is not one join algorithm, there's many, and in particular in parallel. And the best one, again, depends on the data distribution, and lots of other factors, hardware characteristics. So, and that's what people have started to do. People initially, they started to use distributed caches, invent various kinds of join algorithms on MapReduce, map side joins, reduce side joins with input tagging, and noticed, oh my God, that's all not working out well. And then it got even more absurd. People noticed, this MapReduce stuff is kind of okay, but we need something else. So people started to build languages on top, and then all the hives and the pigs came about. So people were reinventing SQL. That's really a great step, So Mike Stonebreaker, who is the Turing Award winner of this year, he gave a talk some times ago about at a database conference in Wisconsin. I said, your sure recipe for winning the Turing Award, by the way. And the sure recipe is, at that time, he was talking about XML and XQuery. Well, just wait until people use it, and then reinvent relational algebra. That will get you the Turing Award. It has worked once before. And the interesting thing is we are seeing the same problem here. So people started to use MapReduce. Now people notice MapReduce is actually an aberration. So let's do SQL again. So we built Hive, we built Pig. But they don't add on top of it. So this is really very uninteresting stuff, as you can imagine, because they are missing the point. The point is, we already said SQL is not good enough. We need iterations. We need this advanced functionality. And all the people that do Hive or Pig, they're completely missing the point here. But OK, that's what it is. So let's move on. What are other misgivings? Another misgiving is that if you do MapReduce, you're writing your code in usually Java, or that means you're writing some first-order function, which is often called your map argument or reduce argument, right? You've seen those yesterday. And those first-order functions, they actually, you don't know anything about them. The system doesn't know anything about them. So that means the system cannot optimize them, cannot automatically rearrange them. And you have to do very strange things yourself. You have heard about combiners, In a parallel database system like Teradata, you don't have to worry about combiners. Teradata does it automatically, for SQL, of course, which you can do. Why should a programmer worry about this kind of stuff? But in MapReduce, you have to worry about it, so not a good idea. Then, strict MapReduce patterns, they really prevent the optimization of much more complex analysis workflows, because in order to do joins or process even something like a SQL query, you often need a cascade of multiple MapReduce steps. And so, in order to do things like join enumeration, join optimization, and other aspects of selecting the right indexes out of an HBase, you cannot do that in MapReduce. That's again why people build systems on top of that, and building poor man's version of SQL, which is Hive, or poor man's version of a query optimizer, which again is part of Hive, on top of that, right? So it's really, really funny. Okay, that said, that's an issue. At the same time, another big problem of MapReduce is the key-value model. It's a very system-centric model, right? You have a key and a value, and you parallelize on the key. The challenge is now, if you have a complex analysis pipeline, your key may change during the pipeline, right? So if you have a more complex flow. And you lost the fact that you had a key below in a later MapReduce stage, potentially, which means you have to do a lot of shuffling and reordering. And you remember from yesterday's talk, shuffle is the bad guy in Hadoop. So you want to avoid those. But you don't even know when to avoid those. So fundamental issue. And that's part of the key-value model, right? That's a bad idea. So that means you want actually a tuple model, not a key-value model. And last but not least, MapReduce also missed the point, in the sense, just like SQL, it doesn't support iterative algorithms. So that means effectively what we're doing when we're doing MapReduce, we are doing assembly level systems programming as opposed to doing a problem-oriented program like what we did in SQL. And with Flink, the idea was to bring the best of two worlds together. So because obviously there is a good amount of things from the Hadoop ecosystem that includes the seamless scalability, it includes HDFS, as you've learned about yesterday, it includes the efficient handling and scale out of user-defined functions. So the concept of having a map function that scales out is actually a very, very good idea. The fault tolerance that comes with it. And to deal with complex data types, which you can do schema on read, by having those complex functions, it's a very good idea. But, as said, this is really the low-level systems programming. So if you want to make this usable, you need to add some of that stuff that has made database technology successful. That's declarativity, query optimization, and also robust out-of-core processing. So what happened is, so MapReduce had a very simple model. I read data from a distributed file system, I do something, write it back. Very inefficient because I/O is expensive. And another system, now just to compare, Spark, for instance, has a similar problem, because what Spark does also, it reads the data, in this case it's an in-memory system, but it reads it from memory and puts it back into memory. But what you really want is a system that seamlessly moves out of core if the data doesn't fit into memory anymore. So if you have really big data, then you want to have efficient memory management. So that's some aspects that databases dealt with very well, and any Teradata, any SQL Server can do that anyways as long as it's relational. But what we really have to add, and that's what nobody else had done before we started Stratosphere, is we added iterations, because any non-trivial machine learning algorithm is an iterative algorithm, and you will learn a couple with Jeff, I'm sure. And to support advanced data flows and more general APIs. And we came up with a paper that we published in 2010, an extended version of a programming model which is based on second-order functions. I will not go into detail, but you will learn more about that in the hands-on sessions with Ufuk and Max. And also some evolution of that model, how it's been extended in actual Flink later. So we had operators, of course, like a map and reduce, which is the one-dimensional record and group at a time operator that you can scale out in parallel very well. There's an operator for two inputs to combine them together, two inputs group at a time, that's a join, and a co-group, union just to combine them. Filter is a special form of map, but you can reason about it, you have semantics. And there's several other operators, most importantly, the iterate and delta iterate operator. Those are the key distinguishing features that also distinguish Flink, if you wish, or Stratosphere from any other system out there. And now let's look back. So I said the real thing started in 2008, but 1.5 years ago, we decided over this in this case, two of my students who now have founded the company that also Ufuk and Max are working for, they pushed Stratosphere to become an Apache incubator project. So that happened back then. And that was Stratosphere 0.4, where we had this packed API, we had a dataset API, we had this optimizer, which was our key design point, and a runtime that implemented all the technology that is really, really old. But again, Jeff Dean had not used, namely parallel joins, parallel grouping, eager grouping, lazy grouping, and all this kind of stuff in parallel. So they work from Masaru Kitsuregawa and David Divitt from the 90s. And then you had execution local and remote. And then we have moved this on, and that was not just, and by we I mean a large community of people that includes many people here in the room, also students from KTH and others, not only from Berlin, and created Apache Flink. And Apache Flink, what it does, it takes both data at rest and data in motion, so real-time data streams and data sets. So it makes obsolete what in Hadoop is called this Lambda architecture of bringing streams and the data at rest together, because Hadoop, because of its nature, couldn't handle that very well. So bringing that together by talking to Kafka and so on, and you'll see examples of that later, and bringing that with historic data and do data processing there. And the key thing about Flink, and that was also an important point, when you build a database engine, you always, in database systems, it has been established that a very good model for doing that is pipelining. So that is, you pipeline data through a data flow. And that sometimes you create dams, which are synchronization points for parallelization, for re-optimization, and so on. But in general, you try to stream and pipeline data efficiently. And that's has been the key design point of Flink, such a pipelined, massively parallel engine. And again, that's a difference to, for instance, like Hadoop, and tomorrow you'll hear about Spark, which are batch engines, essentially. So they're batching data together and process on batches. So from a technological perspective. And so there is this data flow runtime. So it really executes pipeline data flows. The data comes from various kinds of data sources that you can think of. There's various kinds of execution patterns, local, remote, and running on Yarn, which means integrating it into the Hadoop ecosystem, HDFS, Yarn, and so on. And on top of that, you have a dataset API, and you have a data stream API. So that's also interesting, and that was also a lot of work of that has been done actually also here at KTH in the streaming case, because as said, Flink by design, the way we had designed it in 2008 already, it's a pipeline processing system. And if you do batching, it's actually just creating temp points on the top. But just by design, it's already clearly streaming. And so it's very natural to build a streaming API on top of that. And in this way, you can handle both streams and data sets in the same system in a very natural way. And then you can have run also simple MapReduce jobs. And then there's lots of APIs that are being developed right now, some more stable, some less stable, and you'll hear more about that later as well, that you can use in order to access data from Flink and processes more easily, and both on the data flow side of things and on the streaming and on the batch side of things. I will actually, just for the sake of time, not go in too much detail on the APIs, because you will play a lot with those later on.
It's also, today we will have a lot of work on Flink,
yeah.
But also we'll have Flink streaming later.
That's right. I think on Friday or Saturday there will be some more discussion on Flink streaming. So the only thing, So the only thing I want to point out here is, and you see that already. So this is your favorite Hello World example in big data, which is word count. And what you see here is a word count on a if you wish, a file, a batch, and this is the word count on a stream. And the important thing that you will see, it looks very, very similar. The only thing that's specific to streaming, and if you remember, Jeff already introduced that yesterday briefly as well, you have something like windowing, and then you have to define the windows. So that's the windowing syntax. But other than that, you see it's the same API essentially, right? So that means it's very seamless, very easy to mix data flows and data streams. So this is important. From a technological perspective, what's really happening under the covers? That's maybe interesting, because this is really, first of all, it's a difference to Hadoop. It's also a bit of a difference to Spark, which you will learn later, in the sense that what you do here is you have your program. It's a data analysis program. And this data analysis program is treated similar to how a relational database system would treat a SQL query. And what that means is, the first thing that happens is you really have a query compiler. So we have a compiler on top that has an optimizer. So this is a program, you write them in Java or Scala. Scala is a good choice, also because in general, if you want to do parallel programming, functional languages are a good choice for that. So that means the first thing is, things happen like type extraction, because you want to know what types you're dealing with. If you do that, then you can efficiently create memory layouts and serialize, deserialize the data much better. And then you also extract the syntax of the of that particular program, define the operators, that there's a join, a where, and so on. And that's not executed in either Java or Scala, but actually the system builds internally a data flow graph, which is really a bottom-up graph where the leaves are the data sources, the edges are data operations like data movement, usually either over the network or data movement over from disk, or it's also data movement in memory, so it depends. And the cost-based optimizer then decides what is the right order of execution of those operators, because they sometimes can be shifted. You want to push selections and projections down in order to minimize results early on, reorder them in order to get new opportunities for optimization, decide also which physical implementation to use for a particular method. I already explained to you before, there's different ways to sort, and sometimes one is better, sometimes the other. And also other more advanced things like, and we'll get into that, how you deal with iterations and so on. But it actually creates this bottom-up data flow graph and determines the right execution order. This is the data flow graph. And then this one gets deployed to the runtime. So the runtime, it's there's master and worker, so it follows the traditional master and worker pattern that is common in distributed systems, where the master is responsible for recovery, for task scheduling, and the workers are really executing the particular data analysis flow, and they are having a memory manager. So one key thing is, and that's also a key feature of Flink, there was heavy investment in memory management, because when you implement the system in Java, which is always a bit of a problem when you implement systems in Java, so most people would not do that, because Java is a much more high-level language, right? So you don't have that much control over the machine anymore. But you can actually play a lot of tricks in order to be smarter about memory management. So you cannot use the traditional Java memory management. Otherwise, you would run garbage collection and things like that regularly, which would slow down your operations. So there's a memory manager. It has out-of-core algorithms. So that's a key difference to Spark, for instance, that what Flink does really the same way as a database system would do it. You have in-memory ways of doing a join efficiently. But if the data doesn't fit anymore, it spills to disk. And then it will leverage an external algorithm. And I said it deals with batch and streaming, and it worries about state and checkpoints in particular for the streaming context. So this is one thing. So what I want to point out briefly, so how much time do I still have? Pardon me?
You have time.
You have time? Okay, good. Then I'll use a little bit more time. So what I want to point out first is...
We're going to have a break, half an hour, so you can...
I see, okay. So the effect of optimization, because why am I so adamant about optimization? Why do I think that this is so important? I think it's so important because it keeps the world for the user simpler. So, and many of you will just use that system, right? But it's important to understand what's under the covers. And the idea is you write your data analysis program. And the data analysis program can be a rather complex script. And in the future, you would also hope that at some point of time, this data analysis program is written by generators, not even by humans anymore, right? So this is what's happening in SQL. Nobody writes SQL queries, right? They're written by front-end tools, and you click them together. So what's happening here now is you write this program, and then you can run this program on a sample of data on the laptop. It should run fine. It should run on a large cluster. And it will actually be the same program. It will be executed very differently, but the system will automatically decide how to execute it. And you can run it a month later, and the data has changed, so the execution strategy may again be different. And the system will decide, should it use hash-based versus sort-based methods, partitions versus broadcasts, should it use caching, or should it reuse partitions or sorting among different parts of this data analysis workflow. And why do you want to do this? So this is actually still a fairly simple example of an algorithm. This is a visualization tool. That's probably an older version even. I'm not sure if we still have that one in Flink. Something. Yeah, still pretty similar. Okay, good. So, so this shows you essentially how those operators connect and what operations happen between them. And what you see here, for instance, is those gray boxes. Those are deciding the communication. And this is something, if you were to program in Hadoop, you have to decide those kind of communication patterns if you want to be efficient yourself. Or if you program in Spark, for instance, you have to decide when to materialize your distributed data set. Whereas in Flink, or let's put it this way, in the further vision, and part of it is part of Flink already, the optimizer will automatically decide, how to process those more advanced pipelines. And it's clear you don't really want to hand-tune that. And that's still a simple example. So just to give you a point of reference, and I'm sure Björn would also know that, when you're talking about a real commercial setting, people talked a lot about the real world. This is still almost a toy example. The real world, and now I'm giving an example of a SQL query. So when I was working at IBM, we had a SQL query in an SAP application, and the query plan, the data flow graph that's generated out of the SQL, was actually as big as this screen here, or actually a bit longer, and it was printed in a 12-point font. So it was actually, the number of those boxes were 8,000 that were connected, and the system had to decide in which order to schedule them and so on. So those things can be very, very complex. So that's why you definitely don't want to hand-tune it. And so I essentially talked about this slide already. So you have the parser, the optimizer, and so part of it is interjecting actually with the language compiler. Part of it is part of the stratosphere, or now it is Flink optimizer, and moves that. So I will, just for the sake of time, actually gloss over some slides, because some of that will repeat anyways. So type information is, of course, important. It's used for optimization. I will not go into the optimization. I should say a lot of that, I said there was groundbreaking research that we did there. So a lot of that was published in research papers and has then led to the actual systems work. So data streaming, I actually will also gloss over that because you will hear more about that later. So I will not actually talk about the windowing and so on. The ETL pipelines I also have covered because I want to get to some other things. Yeah, maybe that's interesting. So the memory management, because a lot of work has been done there in Flink. What you see here is when your data size grows, and eventually this is just, in this case, combining two data sets. When the data size grows, so that it doesn't fit into memory anymore, you actually don't get a really bad explosion. It gets slower, but it doesn't get slower like that, which is what you would expect if you don't have graceful methods. And that's also an aspect where Flink, for instance, shines over Spark. So this is just showing you a measurement where you see that Flink, so of course, first the data has to go into memory. So once the data is in cache, then you get a rather robust performance. Whereas in Spark, because Spark so far, of course, I'm sure they will change that eventually as well. But so far, they have not worried so much about memory management. You get some peaks here, and that's as far as I would think because of garbage collection that's happening at some unfortunate moments. Can be fixed also in Spark, obviously, but so far that's also an interesting difference. Table API, I'm sure you will learn, because I want to get to two more things that I want to highlight. The first one is iterations, because as said, any non-trivial data analysis algorithm is an iterative algorithm, be it training a support vector machine, be it building an entropy maximization model. Lots of machine learning algorithms require that. And what you do then is essentially you have a for loop that at some point of time will converge. And the interesting thing is there's two fundamentally different for loops. Both of them would be for loops in your code, but they are fundamentally different with respect to execution. The first for loop is a for loop where you say, do something until nothing changes anymore. Nothing changes anymore. The fixed point is defined by, I have a lot of elements and each element stays the same. Right? So that means I could have my termination criteria like the delta over all elements which I compute by building the difference from the previous iteration for each single element, let's say in a huge matrix, does not change anymore. Then I'm done. This is what I call a bulk iteration, because during each iteration you are recomputing every single element of a matrix, for instance. Very common in many machine learning algorithms, and I'm sure you'll see some with Jeff also. So that's a bulk iteration. The second type of iteration, fundamentally different, is what I call a delta iteration. And what a delta iteration is, it's an iteration where you say, I continue until no new data is being added. So while delta not equal to the empty set, different termination condition, because what you do there is, you every time add data. A simple example of that would be a transitive closure computation. Because if you think about transitive closure, if you have A, B, B, C, and C, D, the next time you add something in your iteration, you find that A, B, and B, C connects A, C, so I add A, C. I also add B, D for the same reason. And then I only have to check those two with the ground truth, and then I can find out that I have to add AD. So that means the amount of work I do in each iteration gets less and less. So in a bulk iteration, the amount of work is the same, whereas in a delta iteration, the amount of work in each iteration will get less and less. And that means if I'm smart in my analysis, if I'm smart in my execution, I can do much, much less work in a delta iteration. However, this requires the system to know about iterations. It requires the system to reason about iterations and recognize that this is a delta iteration and implement it efficiently. And that's a key thing that also distinguishes, for instance, Flink from Hadoop and Spark again. Flink has this concept of a delta iteration integrated. It's not really anything new fundamentally. So database systems for recursive query processing in SQL actually have done that also for some time. But we have taken this to this parallel level. And just to show you what the key thing is between deeply embedding iterations as opposed to having them shallowly embedded, let me show you what, for instance, Spark and Hadoop are doing for iterations. So what Spark and Hadoop are doing, you essentially execute what we call a step function, which is really what you do in each iteration, doing some computation that updates your elements. So you read your data from somewhere, probably disk, you execute a step function, and then you put the result, and now it depends, either in memory, that's Spark, or on disk, that would be Hadoop, and then you do the step again, and you keep doing that, and the client controls the loop. So there's a client program outside that controls the loop. The client is very, very obvious if you talk about Hadoop, because you have to write a driver program outside that calls those MapReduce functions. In Spark, it's a bit more hidden, because in Spark, it's still a for loop, but the for loop is executed actually by the JVM and not by the Spark system. Spark still works for the bulk iterations fairly well, because, of course, having the data in memory, and then you read it again from memory for bulk iterations, that doesn't make a big difference, so you're very efficient, right? However, and we will see that it makes a huge difference once you go to those delta iterations. Because in those delta iterations, and that's what a lot of graph algorithms actually have, so that's what makes this interesting, you actually will have an initial solution, and you will replace the partial solution, and then you will, so that's a general iteration. Go here. So what you can do is with the delta iteration, you can actually optimize it more efficiently, in the sense that you can do things like cache loop invariant data, you can maintain the state as an index and move it further down. So this is a physical implementation of an iteration. So what this really means, and you will see that, you will get a drastically improved performance. So here, this chart will show that you actually do a lot of work initially, and in the future rounds, you will do much less work. Whereas if you would do a bulk iteration, each time you do the same amount of work, which is here on the top. So this is yields very fast graph analysis. And here you see, for instance, 30 iterations in Hadoop, that's just an example, would take that long. Whereas in Flink bulk and Flink delta, and the interesting thing is if you add 61 iterations for the delta, that hardly adds anything because you don't have to do too much more. Okay, so I want to close with just one more thing, so I will spare you that. Yeah, exactly. So just one more thing. So the Flink community is growing, but I want to finish with a little story, and I would like to tell you a story about what can we learn from two Roman generals about big data. So, and in this case, we have two Roman generals. They are called Marcus Pessimus and Gaius Optimus. And as said, they are Roman generals. So here you see a map of parts of the Roman Empire. So you see here nowadays Italy, here Rome, you see Germany, you see Gaul, nowadays France. And so what can we learn from those two? So let's assume there's two Roman armies, and they are in Germany, because you have to remember back then the Germans were really barbarians, right? The Germans were Germany is uncivilized. They were they were not part of the Roman Empire and always making trouble. So that means Caesar would regularly have to send legions there, to pacify the country. So, and let's say there's those two legions led by Marcus Pessimus and Gaius Optimus that are in Germany. And now Caesar tells those two generals they should come to Rome. So they have to bring back the armies. And the problem, however, is, of course, the barbarians. Because you have those barbarians that would regularly attack the Roman legions. And now the challenge that the general, of course, has is how do I bring my troops safely back to Rome? And the two generals have very different strategies. So that's the strategy of Pessimus. So Pessimus is essentially saying, okay, I build a fortified camp. Here you see one of those standard Roman camps, right? You all know them from the corresponding literature. And so you build those fortified camps. And then when the barbarians attack overnight, then you are in the camp, you can march out, deal with the attack, you go back to the camp, and then you continue on the next day. Good strategy, right? And you will eventually arrive in Rome and you regularly build your camps. Maybe not so good for the trees, but that's why a lot of parts of southern Europe have not so many trees like we have here, where the Romans were not, I guess. So, so another strategy would be the one that Optimus is doing. So Optimus' strategy is, you know what? Forget the camps. What I will do is, whenever I see barbarians, I will just proactively, I'll go after them, I'll chase them. So I leave the Roman road that leads me to Rome, and I'll run after them. And once I have chased the barbarian, I'll fight them off. Then I will just walk around till I find the next Roman road, and I'll follow that road and I'll get to Rome. And exactly, now that's the question. Why does this strategy work? All the roads lead to Rome. So it doesn't matter if you turn left or right, you will always get to Rome, right? Because as we all know, all roads lead to Rome. So that means all roads lead to Rome, so it does not matter in which direction you follow a road. Once you have left the road, as soon as you find the road again, you will be fine. So now you probably all wonder, what the hell does that have to do with big data? What the hell does that have to do with data analysis, right? Well, actually, but before we answer that, let's say who arrives faster? And you could argue that very likely Optimus will arrive faster. However, it's not 100% true, because like anything, and the ones of you who are still students should remember that, what's the correct answer? It depends. Very good. That's most of the time that's the correct answer. So that's very good when you have oral exams. You should always know. Very likely the answer is it depends. Now, of course, any examiner like me and Saif and others here in the room, the next question, of course, on what?
Barbarian workload.
Exactly. How many barbarians are there? How busy are they? How well do they attack? Right. So that's the thing. So it really depends. So if there is not too many barbarians, then we can safely assume that Optimus will win. If there's a hell of a lot of barbarians, actually Pessimus will win, because Optimus then will constantly roam around between the roads, right? So, very clear. So, but again, what does that have to do with big data? What does that have to do with our topic? Well, actually a lot. And we're talking about fault tolerance. So, the first thing I should say before I start that, my general disclaimer, fault tolerance is actually a bit overrated, in the sense that fault tolerance depends on how often machines fail. And machines are actually, if you don't use tens of thousands of commodity hardware, the failure rate is not so high, but we can get into that in an offline discussion. That said, but it's simple reliability math. That said, there is two principal strategies of how you can achieve fault tolerance. And we need to worry about fault tolerance when machines fail. So the environment that we have here is like, think of your Hadoop cluster, think of your Flink or your Spark cluster, and you have some machines that fail during the computation. So what do we do? So there's two ways to deal with it. The first one, and that's the standard way, and you will recognize immediately that's exactly what Pessimus is doing. You will actually regularly write things to stable storage. So what I'm talking about here, just to give you a bit more context, I'm talking about an important aspect of data analysis, and that is iterative algorithms. I said before, to me the game changer is that any non-trivial algorithm, any interesting algorithm, because otherwise we already have solutions, namely MySQL or SQL Server or Teradata, but anything that's interesting and warrants something like Flink or a Spark is an iterative algorithm. And if we have those, then the problem is you have a long-running computation, you iterate. And in each iteration, during each iteration, a machine could fail. And now the problem that you have if a machine fails, you lose data, and if you have not taken any precautions for fault tolerance, you will have to restart from scratch. Now, what can we do better? So one thing is, and that's the pessimistic scheme, that after each iteration, you will write your intermediate result to stable storage. You will write it into your distributed file system somewhere so that you can recover. That's the pessimistic strategy. So you write everything to stable storage. And that's essentially what you by default do anyways if you do a iterative algorithm in Hadoop, because after the MapReduce phase, guess what? The thing goes into the distributed file system and you read it again. And that's what the driver program does. And the problem with that, though, is so the good news is it's a pessimistic strategy. It works. It actually, if you have a lot of failures, it actually works well. That's also why, Jeff Dean has an absolute point. If we have tens of thousands of machines, because the failure rate is much higher, if we have 10, 20 machines, actually a failure rate will not be that high. But you have a lot of overhead, and that's the observation. So what we did here, we measured how much time in an iterative program do you do actual work? How much time are you spending just writing stuff into checkpoints? Doesn't look good, right? So again, it depends on your failure rate. But if you don't have failures, it looks pretty bad. And now the big question was, and that was a piece of research that one of my PhD students had been doing, how can you avoid this overhead in the failure-free cases? So if we assume that failures are not so frequent. And we came up with a scheme that we called optimistic fault tolerance. And that's exactly the strategy that Optimus is following. So because what does Optimus do? Instead of building a fortified camp, right, which is writing stuff out, what Optimus is doing, he will actually just try to chase the barbarians and find the next Roman road. And what does that mean? I'll show you here. So if you conduct, for instance, entropy maximization or many other machine learning algorithms, you are solving a convex optimization problem. And if you solve a convex optimization problem, you somehow try to find a minimum, right? So you're following maybe some gradient descent, or you're following some way down to some area. So, and what you do there is, in the failure-free case, you may go down like this in your iteration. Now, what happens if you do pessimistic recovery? You go down this path, and maybe here you write your checkpoint, then you move on, and here something fails. You go back here and follow this path again, which is fine. So this is pessimistic. The optimistic one, what it does, instead of, so I don't write anything. So when I lose something, that means one of my machine crashes, I lose some data. And what data I lose depends on my algorithm. So let's make it concrete. So who here knows, so I hope many of you know Lagrangian methods for optimization. Who knows Lagrangian methods for optimization? Oh, not so many. Okay. Well, I will not go into details, but I would highly recommend you guys to learn about that. That's a very important way of reducing a constrained optimization problem into an unconstrained optimization problem, and very useful, not just in this context. But if you do this, what you essentially have, we have a set of Lagrange multipliers, and the only important thing to understand for this example is each time you change those numbers. So in each iteration, you have a complex formula. Based on the existing numbers, you create new numbers. And you do so until the numbers don't change anymore. And now what happens is, once you have actually lost some of those distributed numbers, right? The vector of numbers is large, some of them on this machine, some on this machine. You lost some of them. And what you have to do then is you just invent numbers. And inventing in this case is, set them to random values. And you continue. And the crazy thing is, the good thing is, and Derek and Radcliffe, two researchers in 1972, have proven that no matter to what numbers you set those, you will actually converge. So that means you will actually, by inventing those numbers, you go here somewhere, but you continue and then eventually you will arrive there. So for iterative scaling, that's this algorithm which is used for entropy maximization, it actually works just fine. And the only thing you have to do is, you have to do what I call a compensation. So you have to basically, the missing numbers, you have to somehow find new numbers. And you find those new numbers using some formula, and the simplest one is just random values. For Lagrange optimization, this works. Now, there's other algorithms where it's not that simple. Another one, and Jeff Allman will teach you that one, as I understand, is PageRank. So we'll learn about PageRank, I think, today or tomorrow. So PageRank, what it actually does, it also iterates. And what it does, it iterates over a probability vector. And this probability vector, think of it when you implemented that in Flink or Spark or Hadoop, you have this large distributed vector, and part of that gets lost. So what do you have to do in order to converge? So the only thing that you have to do is you have to set those numbers again to somewhat random values, but you have to satisfy one constraint. The constraint is all the numbers together have to sum up to 1. As long as that happens, you're fine. And for many other algorithms like ALS, alternate least squares, and algorithms that are used in the recommender systems, that's the algorithms that, for instance, Amazon will use to tell you, hey, you bought this, now you better buy this. So those kind of algorithms also can be mapped to this. So essentially, any algorithm that is a convex optimization problem works. And this is really also what I mean by all roads lead to Rome. Because as long as your algorithm is convex, you cannot do anything wrong. No matter where you turn, you will find the right way. So this is the idea. With that, I will actually conclude. So this is something that's actually not part of Flink. This is current research. We had some papers on that. That's probably more for the PhD student who's interested in that. There's a couple of other pieces of work that we are doing I'm not talking about. So we are really advancing right now, and that's a bit beyond Flink even. We are advancing the declarative programming models a bit further. There's a project that we started that we call Emma. There's a paper, an initial paper on that out here that we had published at the SIGMOD. But this is really the up-and-coming stuff, and we hope that those will also yield open source systems and also new innovations that may lead to company foundations, that may lead to being used in products. Some of it may become part of Flink. So with that, I thank you very much, and just want to point out one final thing, and that is for the ones of you who are more interested in Flink, and I think Ufuk and Max will repeat that as well. There's a conference in Berlin about Flink. It's called Flink Forward. It's on the 12th and 13th of October. So if you're interested in that, there's a special discount code that I was told by Kostas that can be used. In this way, one gets a 25% discount for participating. So if you're interested, learn a bit more about Flink first, see if it's something you might find useful, and if so, you can get much more deep experience use cases. Also, hear about Google Dataflow and Flink and other things. over there. With that, thank you very much, and I think we all have earned ourselves a coffee break now.